Welcome to my YouTube channel Raise a Cat. Myself Yash Mishra, and today in the thermodynamics section we will be seeing the new question in which the initial values are given as the initial width of this system is given as 2 meter and thickness is given as 0.5 centimeter, and there is a steel plate. Okay, so this is an oil bath or the oil tank in which the oil is filled. This is the oil, and in this the steel plate is put on the top. This is in curved shape, and the width which is inside it, but inside width direction we put like cross. So inside width is given as 2 meter. Okay, 2 meter, and its thickness, this one is given as 0.5 centimeter. So inside width is 2 meter and thickness is 0.5 centimeter of this steel plate. Okay, and this is a furnace. Okay, and the density of this steel plate is given as 7854 kg per meter cube, and specific heat capacity at constant pressure is given as 0.434 kilojoule per kg degree Celsius. So these are the values given for the steel plate. Okay, and we have to determine the rate of heat removal which will be required to maintain the temperature of this steel plate as constant. Okay, so we have to determine the rate at which we have to remove the heat from this steel plate to keep its temperature of this steel plate as constant. Okay, so and the T out of the furnace from the temperature, the outlet temperature of the furnace is this 820 degree Celsius. Okay, and oil bath has initial temperature of 45 degree Celsius, and the final temperature of this oil bath is 51.1 degree Celsius. So these are the initial values which were given, and the velocity at the steady state is given as 10 meter per minute. Okay, so this we have to convert it into second. Velocity at the steady state of the oil which is flowing and also touching this steel plate is given as 10 meter per minute. Okay, so we can calculate the mass flow rate as which will be touching this steel plate as density into volume. Density of oil we will take. Okay, so density into volume. Okay, so density into width of the plate. Okay, and this thickness into the velocity. Okay, so this will be volume. So the three dimensions are there: this width and the thickness and this velocity. So it will become the volume which will we can find the volume which will be touching it per minute of the this steel plate. Okay, so volumetric flow rate per minute. So from this we can get the volumetric flow rate per minute, and multiplying it by the density, so we can get the mass flow rate per minute which will be there. Okay, so density is 7854 into 2 into 0.005 into the velocity which is 10. So we can get the mass flow rate in minute which will be there. Okay, and doing the standard energy balance, the whatever the energy will be going inside the system minus whatever the energy going outside the system is equal to the change in energy of the system. Okay, and this the change in energy at the steady state is equal to 0. Okay, because the it has attained the steady state. Okay, or the steady state velocity is being achieved. Okay, so E in is equal to E out. So E in is nothing but the mH plus W, or mH is also equal to mc delta T. Okay, so putting these values mH and work we can work we can relate it by Q. Okay, so because here we have to calculate the heat required, the heat removal rate. Okay, so we related this work from the heat Q. Okay, so mH is mH1 plus Q in is equals to 0 because only the energy or the heat we are removing from the system. Okay, so mH1 plus QE which is 0 is equal to Q out plus mH2. So Q out is equal to mH1 minus mH2. Okay, so H1 minus H2 is equal to C delta T. Okay, so M into Cp into T1 minus T2. Okay, so mass we calculated mass flow rate from this value, density into width into thickness into velocity. Okay, So this will be mass flow rate per minute. Okay, mass flow rate per minute, mass flow rate into Cp value which was given as 0.434. Okay, and this delta T, change in temperature, from it is going to 820. Okay, which was given 820 and the initial was 57.1. Okay, so this was the our final temperature which we have to maintain as 51.1 degrees Celsius, which is at the steady state, and the initial temperature of 820 degrees Celsius. The outlet temperature is given as this 820, and the final temperature of this oil bath which we have to maintain is given as 51.1 degree Celsius. So we can calculate what is the heat removal rate which we have to put so that we can maintain this temperature. Okay. This was the approach. These are the standard formula for the energy balance. Change in energy of the system is equal to delta E system. At the steady state, its value will be equal to 0. And how we'll find this mass flow rate? By finding the volume and multiplying volume flow rate multiplying with the density. So we can get the mass flow rate of the system, and the volumetric flow rate we have to find these 3 dimensions which are there for this steel plate. The width and thickness were given, and the third dimension be related with the velocity of the steel plate, or the velocity of the oil bath which was touching the oil plate. So we found the volumetric flow rate and multiplied it with the density. We got the mass flow rate of the system, or the mass, so which will be there per minute. So and multiplying it with the heat capacity at constant pressure into the change in temperature. Okay, so we can get the what will be the required heat which we have to remove to maintain its temperature constant. Thank you.